As has been said before, my name is Honza Král. I work for Elasticsearch, and I'm their dedicated Python guy. And the significance of that will hopefully become clear during this talk, because this talk is about bridging the gap. When you have something like Elasticsearch, a service, or essentially a database, you need people to use it. You want people to use it and use it from their favorite programming language. So this is a story about how we developed 5 different clients in 5 different languages for Elasticsearch without losing our minds in the process much. So first, let's start with the beginning. Elasticsearch is a distributed search and analytics engine. What it actually does is really cool, but not really relevant for this talk, so I'll skip over it. And go back to our story. The story starts when we decided that we need our own clients. And there were several reasons why we decided that we needed to control this, that we really want our own clients. Previously, there were many other clients out there, community-based. And that's sort of the first point here, the fragmentation. There were many of them, because everyone felt the need, I really need a client, and I don't really like this one for this particular reason, so I'm going to start my own. And so, for example, for Python, we had at least 7 different clients, at least 3 of them fairly major. And that's not ideal, because if someone wants to start using Elasticsearch, they don't know how, they don't know what to pick up. The second one is consistency. I'm assuming that this audience will not be surprised when I tell you that there are people out there who use multiple programming languages. How dare they? And those people typically want to have somewhat consistent experience when they switch languages. So if I work in Python and JavaScript and I talk to Elasticsearch from both of these languages, I want my knowledge to be transferable. I don't want to learn one library for Python and a completely different one for JavaScript. That's just not efficient. So we needed those to be consistent. Also, none of the clients out there were complete or were flexible enough as we would like it to support the different environments that you can deploy Elasticsearch into. Elasticsearch is a distributed thing, so you could have 1 node or you could have 200. You could talk to Elasticsearch directly or through a load balancer. You could even configure the load balancer to do SSL or HTTP auth. And there are many different ways how to talk to Elasticsearch, and we needed to be able to support all of them. Maybe not out of the box, but it should be doable. So, the key aspects of Elasticsearch for the purposes of this talk is that it's distributed. So it can have many nodes, it's a clustering solution, and you can talk to any one of the nodes and it will always give you answers. It talks over HTTP using JSON and a REST API. And it supports various different environments, as I just went through a little bit. Also, the frightening part is it has over, that number is a little old, I believe that now we're approaching 100 API endpoints with almost 700 parameters. So there's a lot of API endpoints. Most people look at this and say, hey, HTTP and JSON, how hard can it be, right? Well, actually, because it's a distributed system, the clients are important. This is actually not my slide. I stole that from Afer from his talk, Jepsen 2, Linearizable Boogaloo. It doesn't say very nice things about Elasticsearch, that talk, but I highly recommend it. And actually, most of the things that he pointed out about us that we were doing wrong, we fixed by then. But this is an important point that he makes, that the client in a distributed system is a crucial part of the infrastructure. Because if you have a distributed system, that means a part of it might go away. For example, you have 3 nodes and 1 will fail. The client should be aware of this and should be able to seamlessly switch and just talk to the other 2. So the client needs to be aware of the cluster, aware of what is in there, and be able to cope. So if you just think that it's just HTTP and JSON, you will typically not deal well in the situation where it really counts. when your infrastructure is stressed, when you start losing nodes and you need to fail over to a different one, or when suddenly you have more capacity in your cluster, but you still keep talking to that one node which you will overload. So that's another big reason why we needed our own clients, to make sure that this is done right, so that people will have good experience using Elasticsearch. Because if you use a tool and the tool doesn't work for you, you're not going to spend the time to investigate whether it was the client or the server. You're just going to walk away. And that's not what we wanted. So that's the reasoning why we decided to build the clients. The next part is, what clients are we going to build? And this is another crucial part, because we decided to just make a low-level client, essentially just the bare minimum, just one-to-one mapping to the REST API. And we decided to build it in multiple languages at the same time, and to make those clients consistent. So overall, the motivation for this was that we want to make the client for everyone. That's why it was low level. That's why it is extensible, that you can switch any parts of it. And that's why it has no opinions. It's all just for the reason that we didn't want anyone to have any excuse to not use this client. So no matter what you do, no matter what's your use case, no matter what's your programming style, no matter what's your tool set, you should be able to use one of our clients and not have any reason to use any other, or God forbid, write your own. That was our motivation that guided us through the design process that we'll talk about later. And lastly, we needed those clients to feel native. We didn't want a Java person to write our Python client. That would make no sense. We needed that code and the API to feel as idiomatic to the language as possible. So we have two a little bit conflicting scenarios. We want them to be consistent, but we want to stay true to the language. So that was a little bit of a problem that we needed to tackle. But the important part is, we started with the 5 different languages, and we chose the languages not randomly. We chose them based on popularity and based on the resources available. And by resources, I mean people like me. People who use Elasticsearch, people who know Elasticsearch, but their primary expertise is in another language. In my case, it's Python. Then we have brilliant guys that do Ruby or JavaScript, or even Perl and PHP. We actually found a person who kind of liked PHP and was really good at it. So that was a major achievement. And that also meant that we were comfortable with offering a PHP client as a first-class citizen, and we're happy to actually support it. So back to the design. We said no excuses. We said that we didn't want anyone to be able to say, no, I don't want to use this client because of blah. We want there to be no blahs. So the first rule that we had were no opinions. Whenever we came to a decision in how do we solve this, the answer was always, we don't. We will only stick to the bare minimum, to the mapping from the HTTP endpoints to the native language. We will not provide any functionality on top of that whatsoever. The reason is exactly because at that point we would have to choose, and our personal opinions would influence the design of the client. And that would be a potential contention point where people would go, no, I don't agree with that decision. I don't want to use this client. And we didn't want that. Now, that doesn't mean that we'll never do it. We're now all working on another set of clients, including me for Python, that sit on top of these, that are very opinionated and that actually make life a lot simpler. And we're perfectly fine with other people doing those as well. There we don't care about the monopoly. Because this for us, the low level, the transport part is the crucial part. That what actually governs the experience. The rest is API, and it's certainly important, but that makes no sense with the constraints that we gave ourselves, especially the no opinions. So that was one part of the no excuses. Avoid opinions as much as possible. The second part was to make everything modular. So to take any part of the client, this is a very simplified class diagram of how the Python client in particular looks like, and allow the users to just inject their own code, their own components into the infrastructure. For example, you want to use different serializer. You're not happy with the choice that I made for the JSON encoder and decoder because you think that you have a faster one. Fine, put it in. You can. I expose all of that through API, through dependency injection and everything, and all the clients do the same. We also try across the clients to conform as much to this architecture as possible. And I'm saying as much as possible because for some languages it's really not. For example, Perl's object-oriented design, if I may call it so, it's really different from Python's. And don't get me started on the differences between JavaScript and Ruby and Python. It's mostly not technical, but it's community-based. For example, Python people tend to be more pragmatic. So I was free to use any tools that I saw necessary, for example, inheritance. I talked to our Ruby guy and he said, hey, I cannot really use inheritance because then it would be frowned upon. That's not cool in Ruby now. So I need to use composition and I need to use different things. So that's also decisions that influenced how the different clients looked like. But in the end, even if they were not classes and the inheritance was not there or there, doesn't matter, the functionality was the same. And the spirit of it was definitely the same. You can take any part of it and switch it for your own. For example, you don't want to talk to all your nodes using round robin. You want to talk to them randomly, or you want to prefer the ones in the same rack as your application and only fall back to the other rack if none of those nodes are available. Those are decisions that you can make. Some of those might require you to write some code, but it's all pluggable back into the client. And we try to expose everything. We also document everything, how this all looks. So again, you will have no excuse whatsoever not to use this client, even if you have some obscure use case or obscure infrastructure. For example, you want to, instead of HTTP, you want to use Thrift or the Memcached protocol to talk to Elasticsearch, which is supported on the side of Elasticsearch with third-party plugins. And here you can just specify your own connection subclass. So how did we come up with this design? So we sat down for a few weeks with the whiteboard and the UML diagrams, and we planned, and then we shot ourselves in the foot. No. We just started with the prototype. We sat down, at least two of us every single time, from two different languages to sort of make sure that we can bridge the gap, that no matter what design we come up for, it will not be custom tailored for one particular language. So the first two languages that we started with was Ruby and Python. Purely because of the reasons that those two guys were the only two client guys that lived on the same continent. And even in the same city. So it was actually fairly convenient. And we prototyped it. We provided a reference implementation, not just to flesh out the design, but also to flesh out the naming, which we didn't really make the best job out of, but it's okay. It's not good, but it's okay. But also that we have something exact to debate about. that we can actually talk to all the other language guys and say, so this is what I mean. Look at the code. It's Python. You can read it even if you write in Perl. Yeah, that's another reason why we chose Python and Ruby, because if we chose PHP and Perl, no one would be able to read the reference implementation. So we had a piece of code that we can reason about, that we could challenge and we could test and we could sort of model the situations what we want to do. So once we had that for at least 2 languages, we sort of standardized it. We created a stub of the documentation for the internal stuff. But this is what we did only for the technical stuff, for the transport stuff. So how do we talk to Elasticsearch? Which component is responsible for encoding the native data types into JSON and back? How do we detect a node failure? How do we deal with retries and stuff like that? Then came the challenge of how do we model the APIs? That's a fairly straightforward problem because, as I repeat, we were dedicated to have as thin a mapping as possible. But we go back to the problem that we had over 100 APIs with 700 parameters, and I don't know about you, but I'm a stereotypical lazy programmer. I don't want to even type if I can avoid it. So 100 methods with 700 parameters, some of them required, some of them not, all requiring a description, a documentation. How do you solve this? How do you make sure that all the clients have all the APIs, support all the parameters, and that everything works? We considered several options. The first one was a reference implementation. That we would dedicate one of the languages, or maybe even write a client in Java so it would be close to the source, to be the reference implementation, and everybody would just copy whatever that implementation did. But the closest at that time we had to a reference implementation, again, was the Perl one, and nobody was willing to read that. Also, no one was willing to commit to maintain the reference implementation. Know that we don't maintain our clients, but we all have different schedules and we have other duties in the company, not just maintaining the language clients. So there is a potential bottleneck where we're waiting for the one guy to maintain the reference implementation. Also, it's really hard to track, especially if you're using with a language that's not that familiar to you. So that is a viable option, but not a very good one. What seemed better to us was to just use documentation. After all our API endpoints are documented in the official Elasticsearch documentation, including all the options and everything. But it's documented for a human. So while it's easier to keep track of it based on Git history and for the individual developers, it's still hard to make sure that it's all there. So what else is there? What other options that we have? Well, we are engineers after all. If we don't find a solution, we over-engineer one. So we created our own API definitions. We use JSON for it because JSON is awesome and everything is in Elasticsearch is JSON. And JSON also has the nice properties that it's both machine readable and human readable as well. So we created a schema for the JSON to describe the API endpoints. We actually got a long way by parsing the Java source code and pre-generating a stub of each of the APIs. That's one good thing I'll say about static languages. Static analysis actually works. So that was very helpful. So we were able to jumpstart the process, create the skeleton of it, and then went in manually and filled in the blanks. So I guess the lesson here is don't send a man to do a machine's job. If you can automate something, automate it. In this case, it also enabled us to further automate the next step. For example, I used the API definitions in JSON to generate a lot of the Python code. I don't use the generated code in production, I just use it to generate a stub, then I edit manually, because I firmly believe in the 90-10 split, that I could generate the 90% and then manually edit the 10%, and it will be better than spending weeks on a perfect tool that can generate it all, or months try to write it all by hand. So how did this API definition look like? It included all the important parts for the API. So all the different URL paths it can talk to, all the different parameters, and whether it needed a body or not. We didn't go further than that. We don't have any semantics there, like what does the body look like, on top of whether it's required or not, and a textual description. There is not enough information to actually validate if the combination of parameters are valid or not. We didn't care about those. Those change way too often, and we didn't want that to be hard-coded. So we did the bare minimum to make it work. And this is how it looked like. This is an example of it. And don't worry, you don't have to read it all. Just the important parts that we have, a link to the documentation, the different HTTP methods that this API can use, the different URL paths, including the description of the dynamic parts in it, the different query parameters, and finally the description of the body and whether it's required or not. So this is something that's fairly easy to read once you get used to the format, and it's definitely super easy to parse and take this and run with it. Also, it's text, it's code. So we were able to stick it into the Elasticsearch repository itself, and now we sort of use it all over the place. Whenever a developer for Elasticsearch makes any change to the API, they also need to change the specification so it's kept up to date with the code. It's in the same repository, so it's possible it also needs to be part of the pull request when you want to change something. We have the scripts to generate some of the clients, and I personally use it to sort of as a shorthand reference to see what all the options are there. So this is the part how we created the APIs. The next part is how do we verify that we've actually achieved our goals? That's always a question in programming, or mostly in anything. So obviously we had tests for the individual clients and for everything else, but we felt sort of unnecessary for all of us to write the tests for Elasticsearch itself and sort of to replicate it in all the clients. And we also needed tests to make sure that the clients are consistent. So again, when we didn't find a solution out there, we started writing our own. So we have a unified test suite now that's actually part, again, of the Elasticsearch repository. It lives together with the JSON specs, and this is how it looks like. To make things diverse, we use YAML for this one, because it actually worked better than JSON. So this is an example of a test. It's part of a file that has a setup that actually creates a document in an index. It then calls refresh, and then it has a test. The test has a do statement, so do something, call an API. We have the name of the API, suggest, and the parameters. And then we have some asserts. In our case, we are just doing matches, so we are doing essentially assert equals. And then each of the clients have code to parse this and run this. And now it even works that if you test against a live Elasticsearch version, we'll query the Elasticsearch to see what's your SHA, what's the SHA of the Git repo that you are built from, and we would download the specs, both the specs and the tests for that particular version, and we would run it. And that way we can make absolutely certain that all the clients are consistent. that they use the same naming, that they have the same set of required parameters versus optional, that they behave the same way, that they throw more or less the same exceptions, or at least in the same places. We also use it to test the server itself, to test that the HTTP interface of the server is not broken. So after we did this and we were really happy with this for the clients, the Java guys came and say, hey, this looks actually really neat. Let's integrate it into the Java test suite as well. So now when you actually compile Elasticsearch and you want to run the tests, it will also contain all these tests that are there as very simple YAML files. This is also the reason why, for a time, I was one of the biggest contributors to the Elasticsearch repository, even though I haven't written a single line of Java code. So it has nice benefits as well. And just to reiterate, so this enabled us to make sure that the naming is consistent across the languages, that they all have the same API coverage, that they solve exceptions in the same way. And we sort of verified that this all worked when we developed the five languages, and then a new one came in. We finally found a good .NET guy, and he just took this. First, what he did was he wrote a parser for the API specs and for the tests, and that already gave him 90% of the test suite that he would need to actually implement the client. So it helped him a great deal in developing a new client from scratch. And we plan to build on this as we find more and more people for more and more languages that are needed and that we are actually looking for. So thank you very much for the talk and for listening to me talk. And if you have any questions, I'm here to answer them, hopefully.
Two questions. What is a typical size of a cluster of Elasticsearch in like node-wise? And what is the biggest cluster of Elasticsearch, node-wise?
The typical is really hard to say. We see many diverse use cases. We see even people who use Elasticsearch and don't store any data in it and just use the percolator feature. So I would say that typical, that would be the long tail, like the 3 nodes. The biggest that we've seen is in the hundreds of nodes, approaching a petabyte of data in size. I'm afraid that's the most I can say.
Okay, so my question is rather clarification. You mentioned about this rest-api-spec. Do you regenerate this with every build, or it was generated once and you update it manually?
We generate it once and we update it manually. The JSON spec itself.
Okay.
Then from the JSON spec to the clients, that depends on the client. For example, JavaScript, they actually don't have the individual methods for the API endpoints. They just have a data structure describing them that they generate from the REST API every single time that the JavaScript client is built. That's also how the JavaScript can support multiple versions of Elasticsearch with the same code base, whereas for Python, I have actually 2 different branches, 2 different versions for 0.90 and 1.0 and forwards. Yep.
Regarding what you mentioned, that the client is part of the distributed system, in your opinion, how far can a client library go in helping the client do the right thing in terms of being a part of a distributed system? Is a good library kind of the ultimate solution in that, or would still there be risks, things that the client has to be careful about?
So in this case, it's more of a defensive argument. It's not that you can save something from the client side. You cannot make a more or less okay distributed system great by providing awesome clients. But you can really break an awesome distributed system by providing and more or less okay clients. So it's just so that the clients don't take anything away from the distributed nature of Elasticsearch. Make sense?
Okay, so how long did it take to write those clients, and were there big differences in times between the languages?
Yes, there were big differences, but the differences were mostly based on the stage when they came in. The fastest one was JavaScript because we found the guy Spencer late in the process, so by the time that he got involved, we already had it all figured out. So that was the fastest. By definition, the longest was the Python and Ruby because we were there from the very beginning to the very end. We released most of the clients simultaneously. So the JavaScript client took I think a month. The Python and Ruby took several months to actually get it all right, and but that was from the early prototype to finished production release. Make sense? Cool. Any other questions?
At first, you mentioned that you thought of building the clients because you wanted to make sure that there are no problems like when nodes go down or something. And I imagine this happens on the clients, although you didn't specify it.
Yes. This happens on the client when there are many options how you can control this. Typically in production, how you would use the clients is you would instruct them, and all clients have this capacity to inspect the cluster, get the list of nodes that are there, and then they'll talk to them in round-robin fashion. And then if one of them goes down, we'll put it on a timeout, and we will not talk to it for, let's say, 30 seconds. Then we put it back into the rotation. And if it fails again, we'll put it on a longer timeout, 1 minute, and so on and so forth. So, and if a node fails, we will again retry immediately on another node. So this is something that the clients all do. You can configure how this behaves. By default, we don't do any of the sniffing. We will still do retries. The reason why we don't do this by default is again tied to the no excuses and no opinions. Because, for example, a lot of people use a load balancer like Nginx in front of their Elasticsearch, and then doing the sniffing won't work. Because if we ask the cluster what are the nodes, there is no guarantee that we'll actually see the nodes. So by default, we don't do the sniffing, but we'll still do the retries and we'll still do the timeouts. Any other questions? Last question, going once, going twice, sold. Okay, I'll repeat the question. Why use JSON for the description of the APIs and YAML for the description of the tests, for the test suite? That's a very good question. We essentially tossed a coin. No. The long answer is whatever was the most readable. The APIs are fairly simple, so we started with JSON and it worked. The tests, when we wanted to stick to JSON, were becoming unreadable very quickly, just from the human perspective and because it's actually written by a human. So it was much more difficult with JSON, so we chose YAML instead because it's actually much more easily writable by a human. So that's the only reason. We chose initially JSON for the rest because everything we do is JSON, but it didn't work for the test, so we found something that worked. That's all there is to it. Okay, thank you very much. Thank you for having me. Oh, one more thing. There is an Elasticsearch workshop that I will run here tomorrow morning. I have no program prepared. So if you want to attend and have some topic that you would want me to address, come talk to me. I'll be super happy for any ideas. Otherwise, I'll just do an introduction, some demos, and an extended Q&A. If you want something specific, I'll be more than happy to provide, but you need to talk to me. Thank you.